first order theory. So what is this? Let me give you 3 examples. So if you work in real algebraic geometry or in complex algebraic geometry, you're usually looking at varieties, which is just zeros of polynomials. So you look at sets of polynomials and look what these things define. And we would look at this, we're working in the real field, but we would also be looking at existential formulas that you can produce with this. So the interval, you can define it using the projection of a variety. So this would also be something that we will be looking at. And just to show you that it depends very much, and it's very, very delicate on the language that you pick, if you look at this structure, which is just the real field with an added sign function, you can define the integers. And if you've heard anything about model theory, I guess you've heard about Gödel's incompleteness theorem. And it tells you basically that if you can define the integers, it's bad. And I'm going to tell you that, in fact, this doesn't imply anything about the above, because we're talking about different structures. So it's important that we talk about everything that we can define with a first order formula, which I'll tell you in a second what it is. And it's very sensitive to the language that we pick. We fix a priori which elements we are allowed to talk about. So formally, we fix a language and then we make all the possible formulas, if you want to think, the things that make sense, using the symbols in the language that you picked, plus the standard logic symbols, which are disconnectives and the existential and for all quantifiers. And one thing, and it's the reason why it's called first order logic, is that we're not allowed to quantify over sets, just over elements. This is not very bad. We always work with a fixed language L, and this is just examples of languages. You can take rings, order rings, exponential rings, all of these things are allowed, just that you know exactly what you're talking about. And a priori, each language in a given structure implied different definable sets. So once you pick a structure, you need to have, the structure needs to know what the symbols mean. If you put a multiplication sign, you have to say what the multiplication means. You look at every single thing that the formulas can say, and there are 2 things that can happen. Either the formula don't have any free variables. In this case, you're talking about truths or falseness in the model. So for example, you can say that every positive element is a square of some other element. And this is true in the reals, false in the rationals. And this is sort of what axiomatic model theory would work on. But where we're going to work in this talk is when you do have free variables. And then what you do is you look at realizations of these formulas, and you associate the formula with the realization. So as was done in standard algebraic geometry, you would look at your variety and look at the complex points in the variety, and you would look at those things simultaneously if you're working on the complex field. So this is our setting. Formally, you give it a model M and a language L, you fix the language, and you say that a set X is definable, and these are the things that we're going to study, if you can find a formula such that this set is exactly the points that make the formula true in your structure. So this is, and now we're going to start talking a little bit more. So what sort of questions do we like to ask about in model theory? So what is the structure of definable sets in a given model? Can you talk about these things? Is there some basic foundational properties? There's something you can say about all definable sets that sort of implies lots of other properties. It's sort of an easy answer to comparing to different structures. And let me tell you one that the answer is no, and it's particularly close to what I do. And also, it will give us to one of the big properties that I'm going to talk about. So if you compare the complex field and the complex exponential field, the first thing that you can see in the complex exponential field is that you can define the integers very easily. And because you can talk about the kernel of the exponentiation, and the kernel is the multiple of 2 pi I times the integer, so you can define the integers. And this is very strange, because if you can define the integers in a field, you're in a bad setting. But somehow, Boris Zilber had this amazing idea that without working in a first order context, you can actually talk about the complex exponential field and say a lot about this field. And you can actually, with Kirby and Angus McIntyre, get a full characterization of how definability works in these complex fields, and you can use it to look at algebraic numbers. Except that, and this is very surprising, you have to assume Shannon's conjecture. So Shannon's conjecture is this strange conjecture about which numbers are transcendental if you mix x's and e to the x's. And somehow this is enough to know the definable structure of the complex exponential field. So, and I'm going to tell you now why the integers are not definable in the complex numbers, and we will define the first foundational property I'm going to talk about. So there are two properties that are very well known in algebraic geometry. One is that if you take a variety and you project it, the image of this variety is going to be a Boolean combination of varieties of the smaller dimensional space. And the other thing that we know is that, well, every polynomial, the zeros of a polynomial are either finite or everything, if the polynomial was trivial. If you mix these two, you immediately get that every definable set, like you do an induction of the number of quantifiers, and you get that every definable set in the complex field, if you look at just the line, it's going to be either finite or cofinite, just in the C. So subsets of C that are definable are finite or cofinite. And this turned out to be an amazing property, and we gave it a name. It's called strongly minimal. And I'm going to say the structure is strongly minimal if any definable set with one free variable, so I'm talking in the universe, in the ground universe, not varieties and dimensional, is either finite or cofinite. And I'm cheating a little bit because you need, not that for any structure this works, but for every model of the theory it works, but this is, let me cheat a little bit. So, and this turned out to be amazing. I mean, this started geometric model theory, and you could recover a lot of the things. So just easily, we can know that the Z is not going to be definable in the complex field. Why? Because, well, Z is not finite nor cofinite. And this immediately gives you that the complex exponential field and the complex field are different in the structure of definable sets. Turns out that the same thing, more or less, happens for the real field. If you look at the real field, every definable subset of the real field is a finite union of intervals and points. This is one of the consequences of a very important theorem of Tarski. So if you think about it, you can define it using just the order symbol and equality. So we give it a name, o-minimal, order minimal, or, as I'll try to talk about this in this theory, less minimal. It just means that using just this symbol, you can define the same subsets of R that you could define with a full structure. This doesn't mean that you can define everything, because you don't know what happens in larger dimensions. Just in one-dimensional sets are the same. So you have these two things, equals minimal and less minimal. And, well, this is the analog for less minimal. And a lot of great consequences happen. And the first one, I'm not going to tell you what it means, but I have to say it because it was the reason why it was invented. And it's that all strongly minimal theories are categorical in any uncountable power, and this is amazing. Theorem of Michael Morley. And one thing that you get is you can also get a dimension. So now I'm not talking, I have this property that tells you how the one definable sets work. And suddenly you look at every possible thing that can possibly define the full universe, and you can have a dimension. It works very much like the Krull dimension. And the same thing happens for a minimal, except that on the opposite side. You can look at topological dimension, meaning like the boxes that you can submerge in your structure. And again, if you know that a structure is o-minimal, so that the one definable sets are intervals and points, then you know that they can define a well-behaved function in all the universe, in all the Cartesian powers. So these are two properties that suddenly start having all this very nice consequences. And they would have been the center of model theory for many years, except that Shella discovered that strongly minimal theories was a notion that could be, I don't know, bettered. So he decided to find this thing called stability. And stability means, remember that order minimal, of course, you have to have an order, otherwise you cannot define intervals. Shella discovered that if you ask that in a structure, there's no way to order any infinite set. This thing had amazing properties. It's called stable structures. And the definition is exactly what I'm telling you. You just take any infinite set, and no formula will order this infinite set. And of course, if you think about it, strongly minimal sets are clearly stable, because if you have an order in an infinite set, you can take the elements that are bigger and the elements that are smaller, and this set will not be finite nor cofinite. Okay, so it generalizes naturally the order. But at the same time as he defines stability, he gives us a way to recover the dimension. But we have to think of dimension a different way. So crude dimension, topological dimension, most of the dimensions that we know are maps from the category that we're looking at into the integers. And it tells you a way to know when something is bigger than the other. But you don't really need it to be a map into the integers. What you need to do to work on, if, for example, to do inductive arguments, is just to know when somebody's more than the other, and that this pre-order is well-founded, that you don't go down infinitely many times. And it turns out that there is a notion like this, and it's called forking. And this is the definition. If you have, I'm going to give you pictures in 1 second. If you have a smaller set inside a bigger set, I'm going to say that it's smaller if it somehow is, if this thing is somehow fibering this thing. And what it means somehow, it means that you can find an infinite sequence, all of which are elements of the bigger set, and that hopefully they don't intersect at all, and you have fibers. But maybe they intersect, but in smaller sets. Okay? If you look at the definition of this, you will get something different. You will find that it means you need this family to be K inconsistent. But I think in the same notion. So it's an inductive argument, and you know what is smaller in the, yeah. So here's the picture. You have, say, a variety V of x defined over Q, right? And using pi, a transcendental element, you find some fiber that is inside. If you take another transcendental element, you will have another fiber that is in the same variety. If you can find infinitely many of these, such that either they don't intersect or intersect in finitely many sets, then we're going to say that the fiber was smaller than the variety. And this was an amazing notion. It gave us everything. It gave us inductive arguments, but it gave us much more. Like everything that's going on in stability theory, which is a lot, is based in forking. This is a really, really core notion of model theory. And it's really recovering what we had before. It's recovering this Morley rank that we had for strongly minimal sets, which is what I meant as an analog of the crude dimension. So it's worked very well. And stability theory was at the center of model theory, at least until the 90s. And probably the main applications to mathematics have been all the proofs using stability theory to Diophantine number theory. And the most well-known is Hrushevsky's Mordell-Lang proof, which, if I could resume it in 2 minutes, it would be like this. Manin, to prove basically you want to understand, you have an abelian variety and you want to understand a finitely generated group and its interactions with algebraic varieties. And the way Manin did it when we were working over function fields is he made a derivative, inserted a derivative to the language, which didn't exist before, and somehow captured this finitely generated group with its derivative. And somehow he, using the properties of this derivative that he had defined, showed that when you could relate it or not to the original algebraic structure and therefore to subvarieties. And what Hrushevsky did was realize that really had very little to do with the actual properties of this derivative. It had to do with that the structure you defined when inserting this derivative was stable. And when you have stable structures, in many ways, you know, many times you know exactly when your structure comes from the original algebraic field and when it doesn't. So he could take Manin's proof and first sort of simplify it a little bit, but also he could do it for characteristic P where you don't have derivatives, but you made some other structure that captures this final generated group and tells you when it comes from the subvarieties and when it doesn't. So it's really amazing, and stability is at the core of it, or we would think so. So on the other side of the spectrum, you have o-minimality. And o-minimality doesn't have this nice notion of generalization, so we actually work with o-minimal structures instead of going to some more general setting. So o-minimal means that on the ground, over the ground structure, and for a minimal structure, we will always talk about R. So on R, every definable set is finally unit of intervals and points. And it really started as a foundational question, and this is something that I really like, because it was Pillay and Steinhorn that started asking themselves what properties that we know of the real field are due just to o-minimality. How much can we recover just from knowing that it's o-minimal? So they didn't have any other example. Well, just the additive ordered group, but no other very significant example, but somehow they really studied what you could do with this. And you could get a lot. You could get dimension, you can get piecewise continuity. By this I mean, because you have an order, you have a natural topology, and you have piecewise continuity for every definable function, you have piecewise differentiability, you can triangulate, you can find Euler characteristics, you can do everything you want for definable sets, which is our category. And it turned out that in many ways, what o-minimality is giving us today, although it may have other applications, is it tells us what analytic functions you can add to the real numbers without losing nice algebraic properties. And the reason I say this is because there's a lot of o-minimal theories, and this is something that we found later. First, Wilkie proved that the real exponential field was o-minimal. So all these properties that we knew for the real field were true even if you had exponentiation. And then Speisecker generalized this result to show that the Pfaffian closure is o-minimal. I'm not going to tell you what the Pfaffian closure is, but basically means that you can add something that we call Pfaffian differential equations to the structure and you keep the nice properties. And just to let you know, every integral is Pfaffian. So you can add every integral to this field. Anything you can define here and their integrals will be o-minimal. So you can take basically any probability distribution that you want and you will be able to insert it in your structure, preserving o-minimality and keeping all these nice properties that we had. And this again had very nice applications, and probably the most well-known today, it's again something for Diophantine number theory, and it's P-less and conditional proof of the Andrew conjecture. And surprisingly, the scheme is, again, in 2 minutes as follows. You want to understand rational points in some variety. What you do is you add extra structure, preserving o-minimality. Now we are working on the real numbers, and you look at your variety, say over R squared, if it's a complex variety. And then you add this extra structure that captures your rational points. And then you prove, because it's o-minimal, that the rational points live mostly either in a subalgebraic variety, so forget about the extra structure, or there are few of them outside the subalgebraic variety. And then you work with the few ones, and you work with the big ones, and you prove whatever you want to prove. And there's been a couple of applications from Pila of this theorem, and it's fantastic. Okay, but the application that I'm going to talk about, it's a different one. And it has to do with VC theorem. So what is VC theorem theory? It starts with a problem. The problem is you have points in your space, and you take random sampling, and each time you pick a point, you know if it's a good point or a bad point. And you want to separate your good points from the bad points using some element of some family that you have fixed a priori. So say you have lines, semiplane. So here I can separate most of them. I have 3 errors. Okay? And the question is, well, what does this tell me about how good this line separates points whenever, like in general, for all the possible space? So because I picked this line after looking at the points, it's a very sensitive question, and it's not very easy. But there's a big theorem that is Vapnik and Chervonenkis theorem, which tells you the following. So this F is the family that you're allowed to pick things from. So it's we're going to call it potential classifiers. We're going to find some function that goes from n to n. I'm going to tell you in a little bit what it is, such that given any F in your family, any L in your family, and a random sample of n elements, then the real error of L, the asymptotic error of L, the error that happens when you take all your probability space and start picking elements, is going to be bounded by the one that you're looking at, even after choosing, plus some error. But this error is going to have this log 2 delta over, this delta is just means if you're very unlucky picking your sample. So this is sort of a constant. It is a constant. And this thing here, if you look at it, is your function on 2n over n. Now your function is going to be either polynomial or exponential. And if it's exponential, well, you didn't do anything, right? Because the n comes down, it cancels, and you get some huge error, which is bigger than 1, so you really didn't do anything. But if it's polynomially bounded, then the exponent comes out, and you get log n over n. So this is going to converge. And as I show you, going to converge pretty fast. So the question now, if you want to apply these things, you need families that you know that this phi is polynomially bounded. Now let me tell you what this phi is. This is how you calculate the phi. You choose n points in your space, and you look at how many different subsets your family F can choose from these n points, and you count. And that is going to be this number here. So it's at most 2 to the n. But then you have to maximize over every possible endpoint in your space. So that's hard. And after that, you have to do it for every single n and look at if the function that you're getting is polynomially bounded or not. So this is really hard. And in fact, you can prove it for semiplanes, and that's hard, but not too hard. And most of the applications that I've seen have been showing that because it's polynomially bounded in the semiplanes, in any dimension, you could transform the family of semiplanes to things that are a little bit more interesting and show that it happens there. So, for example, using Veronese transformations, you can get that every polynomial, if your polynomial is bounded, you can find a bound for this. And I'm technically cheating a little bit, because it's not only semiplanes, but it's any positivity set of functions embeddable in finite dimensional spaces, which is more general, but it's still, we can do better. Turns out that Karpinski and McIntyre, and afterward, they didn't state it like this, but it was stated like this in a paper, really nice paper from Aschenbrenner, Dolic, Haskell, McPherson, and Starchenko. They showed that if your family was definable in a minimal structure, it was polynomially bounded. And not only that, but you knew exactly what the bound was. And the bound was just the number of parameters you were using. So for example, in the semiplanes, the function phi of n is going to be bounded by a polynomial degree 2 because you're using 2 parameters to define semiplanes. And well, this was the one that we knew. But to give you an example where it's really hard to find this family, the function is going to be bounded by polynomial degree 3 because you're using t, k, and lambda as your parameters to define the family. And this was something that this was an actual family they found in a paper of statistical learning theory, and the bound that they had was 16. So it was a significant improvement of these things. And I'm going to tell you 3 things about this. First, there may be many other families that they will have nice bounds that you can see with minimality, but we haven't discovered yet. But it's really hard to find because if nobody could prove that they were polynomially bounded, nobody used them. So yeah, so we have to find it. But the bounds that we're getting for the existing families are really, really nice. And somehow this Vapnik-Chervonenkis theorem was used for at least 2 things that I know of. One was learning theory, like you could train a machine to start picking the best semiplane, and you could learn it to teach it to identify A's from non-A's, and it's actually been used for this. But another thing that was used for was understanding the complexity of a family. So if you're going to do a model selection, and you have different families from different complexity, how do you punish the complexity when choosing the right model? And this was called structural risk minimization. And it seems that because the bounds that you were recovering using standard Vapnik-Chervonenkis theorem were so large, you were over-punishing the models. And that using the bounds that we're getting, we will get something much better. I should say that it was incredibly lucky. When this theorem appeared, this last paper appeared, I was working on the model theoretic side of this, which is called DP-rank, which I'm not going to tell you about, but it's also really, really nice. And at the same time, my university decided to hire a statistician. And they hired this amazing Venezuelan person who happened to be a student of Dudley and more or less the Latin American expert in statistical learning theory. And not only that, but they sat him in the office right next to me. So we started this collaboration, and it really seems that you can get a lot of things, although even though promising, it's not conclusive, so this is ongoing work. This is what I'm going to tell you about o-minimality and stability. So let me recap what we were saying. And I want to recap it using one description that Hrushevsky did, is that model theory is the geography of tame mathematics. And in this context, stable theories tell you what tame algebraic structures are and how they behave. And it really captures algebraically closed fields, vector spaces, most of the things where you think about as algebraic. And somehow, it also is starting to capture what the tame topology over the real line would look like. And I only mention analytic expansions because those are the ones that we have most general theorems of what they work. But if you have any curve and you feel that this is a function that doesn't behave too badly when you add it to the real field, you can see if it's so minimal and you recover a lot of the properties. And I hope that I was able to show you this, but surprisingly, things that happen in stability theory and minimality happen, the same things happen in both sides. You have applications different time number theory in one, you have applications different time number theory in the other. You have dimensions in one, you have dimensions in the other. You have a group structure in one, you have a group structure in the other. But the methods were completely different. And this is, I think, what made me decide for my PhD thesis. There should be some way that you can have these two contexts work together as opposed to inspiring one another, but completely different methods. So this is what I work on, concentrates on settings and notions that generalize and work well in both minimal and stable theories. And the questions in this direction are, for example, can we give a uniform definition of dimension? I'm going to tell you why forking does not work when you have an order in 2 seconds. So it doesn't work. Can you find something else that does work for both sides? How do stable sets in minimal structures behave, and how does forking mean outside stable theories? Like, we have this really important notion that somehow it would be unbelievable that it would only work in this very restricted setting. And is there any nice setting that generalizes minimal instability? Actually, this was answered before I started working on it. I'll tell you later what it was. So forking. What happens with forking outside stable theories? What happens if you have an order? In particular, what happens in minimal theories? I'm telling you. So you have an interval in a line. And of course, they both have dimension 1. So clearly, this is not dimension smaller than the line. But it's clearly forking smaller. But because you can translate your interval and find things that look exactly the same, and you're sort of fibering your line. So the interval is forking smaller than the line, but it's not dimension smaller, so at least it's not capturing dimension. So how do we fix this? So what we did was suggest an alternate definition of forking where you still have fibers, except that you can't just pick any fibers you want. You want real fibers. So you want to have a definable set, an object mark category, that if you look at everything that comes from this, you actually get this small intersection property, okay, that is defined inductively. And actually, you can define it, being k inconsistent, it's easier to define, but I think it's a little bit less practical. So what happens here? So again, I want to show that this fiber of my variety is smaller than the variety theta of x. But what I have to do now is I have to look where my parameter lives, find a neighborhood of the parameter for which the point is not an isolated point, and then show that if you pick any number of points in this neighborhood and you look at their fibers, their intersections will be small or will be empty. So if you think of topologically, this is exactly what happens in topology, right? Like, but you have even empty intersection. Like, you have actual fibers. Here, this definition doesn't quite work in general, but if you allow it to have small intersections, then it's perfect. So this is the definition of Thorne forking. And actually, it works exactly as I suggested. It recovers the dimension of a minimal theories and recovers stability for, forking for stable theories. So you have probably the two main concepts in both sides of model theory characterized by Thorne forking. Let me tell you why now we don't have the problem of the line. Let's say that you wanted to show that Thorne forking, this was smaller than the line. Well, you try to, so you look at where your parameters live, and you look for neighborhoods around the parameters. But if you pick any elements that are close enough, they will intersect your original segment in a very large set, right? Because if you have small deformations of A, the interval will be only slightly moved. So you will have a very large intersection, so it doesn't Thorne fork. So that's the reason why it works well in minimal theories, because you actually need like geometric fibers to show Thorne forking. So this was my PhD thesis. And later, I went to the next question, is what is happening with forking? Actually, this was studied more or less at the same time as my thesis by Alf Onshuus, and he looked for o-minimality. There is some sense in which the interval is smaller than the line. And this is being captured by forking, but what is the sense in which the interval is smaller than the line? And it turns out that it's the following sense. If you give the interval a measure, and a measure that behaves well in translations, well, if this has positive measure, the line will have to have infinite measure. And if the line has non-infinite measure, this has to have measure 0, because otherwise, translations of this interval will guarantee that the measure of the line is very large. So this notion of incommensurability is being captured by forking, actual forking, the original version. And it has amazing applications, and it's been used by Krusowski-Pillay, Simon, and others in understanding what happens. So forking is interesting outside stable contexts. And in fact, the fact that forking and non-forking coincide, I think it's very close to the fact that if you take a complex algebraic variety and you look at the complex points, the topological dimension and the crude dimension will coincide. And so it's an actual very deep property of stable theories, the fact that non-forking is capturing forking, and it should have nice implications. Now, let me tell you what dependent theories are. Dependent theories are something that generalizes both stable and minimal theories, the one that I promised you. And it actually means just that this phi sub phi function is always polynomially bounded for anything that can be defined. So all this thing that was happening in combinatorial theory was also happening in model theory somewhere at the same time. I'm not going to talk about this much more, but I wanted to give you the definition because everything I'm going to say from now on will happen inside stable theories. So now, let's look at a naturally mixed context before I continue to the talk. So, I think this is the easiest valued field. So if you take your standard Lorentz series, I think it's the ones that start with minus something. Well, yeah, this. Then you can find a lot of the structure by sending a map that sends any series to the first I with coefficient non-zero. This always exists. And you have a residue map from the Taylor series into the residue field, which has valuation at 0. So you take the series where the valuation at 0 exists, and you project and look at the valuation in the ground structure. So somehow you have this, you can think of it as this two-coordinate system. On the one hand, you have the valued group, which has an order, and on the other hand, you have the residue field, which in this case is very nice. It's a complex number, so it's stable. It's the prototypical stable theorem. Well, Z is not a minimal. But, sorry, first of all, I'm always going to look at value fields at this three sorted setting. So the field, the map here, and the map to the ground field. And Z is not a minimum. And in general, in model theory, we've learned that if you take algebraic closures, things are nicer. If you take algebraic closure of that series, you can prove that if you take a valued field, there's always a natural way to extend the valuation and the residue map to the algebraic closure. If you take the algebraic closure of the Taylor series, you get this, which are called the Poisson series. And the valued group is just now going to be Q, which is so minimal, and you get, again, your algebraically closed setting. So this is a setting that has stable and or minimal on both sides, or not. You actually define many of you know what this structure looks like, and Dietrich Haskell, Uri Hrushevsky, and McPherson proved that you could actually understand even the quotients of definable sets. So you can say a lot of things, and this prompted a research that actually has some nice implications in mathematics. One is Hrushevsky and Martin's proof of rationality of certain set of functions of the periodic field, and another one is there's something that Kontsevich proposed, which is called motivic integration, and you can actually redefine it by looking at these properties that you had that Haskell, Hrushevsky, and McPherson had, and get a lot of nice implications. But let's move on because I want to look at stable settings. So this theory is not stable. You actually have an order going on. Well, can you find what about the stable definable subsets? Can you localize stability in some sense? And the answer is you actually can, and it works very well. And you just remember the definition of stability is that you cannot order any infinite sequence. Well, you can define local stability as that you cannot order any sequence inside what you're looking at. And it works very well, and in fact, you can use it to characterize a lot of what's going on in stable structures that arise from minimal settings. And by this, I mean like how the complex numbers arise from R squared. But it is not enough in our valued field setting, because in the valued fields, there's not enough stable structures. There's just the residue field. There's nothing else. In order to move on and look at some stability that is significant, you have to move into types. And let me tell you what types are. And this is probably besides stable o-minimality and forking, it's the third most important notion in model theory. So in the classical setting, when you were looking at algebraic varieties, you many times take variety over Q and take a generic point, generic realization of this variety in some larger field. So, for example, E and E squared and pi comma pi squared are both points of the curve y equals x squared, and they don't satisfy any other polynomial over the rational numbers. And they behave very nicely, and you can choose either of them. They both satisfy the same polynomials by definition. You want them to satisfy whatever is implied by y equals x squared and nothing else. But you can also have an automorphism of C that fixes the rational numbers, which is what you want to study, and sends one tuple to the other. And this is still true for types. So types for us are going to be infinite definable sets. And they're sort of, you can look at them either at all the sets of formulas that are realized by a tuple, or you can look at it as the orbit of your tuple in a very large structure that fixes the ground set that you're trying to understand. So these are types. So they're sort of like definable sets, but much smaller, infinite definable sets. And you can, again, try to look at your definition of stable types. And again, it's going to work fantastic. But again, if you wanted to understand valued fields, algebraically closed valued fields, it's not enough. However, Shella came up with an alternative definition. And it's, let's not ask for this order thing to happen, but let's take the most important property that we have, which is forking, and ask that the realization of the type behave nicely with respect to forking. And you just need it to be symmetric. So if you think of independence relations, they're usually symmetric. And this is what you ask, and this is the definition of something called generically stable types. And these are a fantastic element for algebraic closed valued fields. So first of all, they behave very nicely. So we were able to prove with Alexis Biatsov and the Garcia student of mine that this whole forking and Thorne forking coincidence happened again in this very restricted setting. And Dudry Haskell, again, Haskell, Krzyzewski, McPherson, sorry, there's an extra Krzyzewski here, which shouldn't be, in a different paper than the one I mentioned before, proved that the forking relation, this very important notion that we had for stable theories, was very significant even in this setting, and that if you were working generically stable types, this independence could be traced down to the residue field. So you can understand it very well, and it had very, very important properties. And in fact, we found that this domination has very alternative definitions, and you can find like stable halls of any type that you want. So it's a very important notion, and there's a lot of work being done on this, and I'm just mentioning a couple of the things that I have done. But let me tell you how important this is. So change of pace completely. If you take the p-adic elements, or if you take its algebraic closure, so the natural algebraically closed valued fields, they are totally disconnected. And this is easy to find. Like the valuation is an ultrametric, and you can find balls, there are disjoint balls everywhere you look at. This means that you cannot take paths, and this means that you cannot like look at analytic continuation, connectedness, well, the standard cohomology theory and multiple types. All the things make no sense when you work in this setting. So Tate started to look at these things in the case of elliptic curves, and he showed that for elliptic curves you could add points to the space in order to not make it totally disconnected and somehow recover a little bit of what you got when you look at the complex points of a variety. So you could have paths, and you can start looking at well, all the topological properties, just looking at path connected and the simplices and all these kind of things. Berkovich found a way to do this in a more general setting, and he defined a space called the space of seminorms, which is a pretty complicated object. And he was able to prove that in this space, it actually recovered what you wanted, but only for smooth varieties. His proofs were not able to get past ramifications and what the residue field was, and it depended a lot, and it really depended that your variety was smooth. Singularities were a mess, and you couldn't really do anything with them. But at least we had an object, in some cases, where you could recover something that behaved topologically as V of C relates to V of X, which is something that you wanted very much. Turns out that what Berkovich was doing was looking at generically stable types. So Krzyzewski and Loeser proved that if you take a variety, and remember that types are just infinitely definable sets. So you look at infinite definable sets that contain this variety, that live inside here. And you look at the ones that behave nicely with respect to forking. So these are the generically stable types. You have a space, And because of the nice properties of the generically stable types, you can actually define a topology in these things, and you can find a very, very nice topology. And turns out that Berkovich objects were very naturally inside this space. In fact, you have a natural surjective homomorphisms into this Berkovich thing, and you have a natural topology. But these were algebraic elements. These were things that we defined from model theory. These were things that we were studying from model theory, that we understood very well from model theory. So we had a much better grasp on what they were than Berkovich had. And in fact, you can get Berkovich's proofs without assuming smoothness, and I think in a much more natural way. So this, I think, it's the most important theorem, and it basically tells you that you're really recovering the topology. So you have, if you have any semi-algebraic subset, you have a finite simplicial complex of dimension less than or equal to dimension of x and a strong deformation retraction from this thing. Sorry, I meant this is x.
X is u.
See, if you take x a variety,
Okay.
then you will find a simplicial complex, which is a subset of the, I mixed u and x, I'm very sorry.
Okay.
Which is a subset of x and dimension less 1 or equal to your variety, and you have a strong deformation retraction from x cross 0, 1 to delta. So you really have, this is path-connected space. I'm very sorry, no. Here's what x is. So you have your variety, x, and then you take your completion with generically stable types. And this is what you call Vn. And for anything that you have inside there that you can define in a natural way, but now you're not looking at the points in QP, but you're looking at the points in these new things, the generically stable types. So this is U. So this U relates to X in the sense that you're looking at points that were in your variety, but were in this completion thing. And from this space, you have a strong deformation retraction to delta. So you can actually look at the simplices, the complexes that you're defining. You can do homotopy theory, you can do cohomology, you can do whatever you want on the spaces in the Berkovich. And this is the actual Berkovichification. It's just that the proof involved looking at generically stable types. But we're talking about the same objects. It's just that we understood them in a different way. And in fact, it really behaves like the complex analogy. So you take a complex algebraic an algebraic variety over the complex numbers over Q, and you look at the complex points, you're looking at a topological space of dimension 2 times the dimension of the variety. And you look at the topology that happens here, and you can say things about the opposite side. It turns out that this Vn actually lives in not R to the 2D, but R to the 2D plus 1. So we basically recovered in the more general setting everything that we wanted to recover from this analogy from complex to the p-adic case. And let me finish with a couple of thoughts. And it's in everything that I've told you before, somehow there was this movement in model theory, this study of certain objects in model theory that we studied just because they seemed nice. Like we studied o-minimality because I want to know how much can I prove with this particular concept. We study generically stable types because, well, they live everywhere and we want to see what properties they have. We study stability theory because we could retrace many of the things that we wanted for the saturation problem, but in a more general setting. And somehow these natural either objects or properties or theorems that we study because they seem natural, well, they will probably turn up in many areas of mathematics because nice and natural objects tend to show up. And model theory is a very young subject. We've been around for most 50 years, I think. And somehow, I think the interactions of mathematics are just starting to show up in a massive way. And this is the reason. We look at foundational problems, but foundational problems usually tend to have really significant notions or objects that will show up in general. And this is sort of what I want to tell you from the talk. All right.
there any questions? Questions, comments? I have a small question, but we have to go
Back?
to several slides. You had an example where you have this series starting from -m to.
Ah,
Is there any?
here.
Is there any sense to have instead of p to the power I polynomial there? Polynomial for the I?
Yeah, well, yes, and it's so. Yes, but I guess there are two things. One is in like the field of rational functions, like if you just take the inverses, and actually model theoretically they're equivalent. You can define one from the other. That is not a tame object. That is a hard object, and yeah, you can show that it's what we call Gödelian. So there may be ways to analyze it model theoretically using tools that sort of capture the Z, but it's not. It's at least we don't understand it well yet. Let me take that for the rational functions.
Any other comment, question? Well, let's